Okay, so I saw this experiment online the other day, and it really made me stop and think. Someone dropped an ice cube into water, and it just sank straight down.
Ah, yeah. That sounds like it wasn't just any ice cube. It was probably made of heavy water.
Heavy water, so not like, hard water with mineral.
No, no, totally different. We're talking deuterium oxide. It's chemically distinct. Today, let's dive into that.
Okay, let's unpack it.
Yeah.
So normal water, H2O, uses regular hydrogen, right? Just a proton.
Exactly. But in DERO, those hydrogen atoms are replaced by deuterium. Deuterium has a proton and a neutron in its nucleus.
Ah, so that neutron makes it heavier, roughly double the mass of regular hydrogen.
That's the key. And that extra mass changes, well, pretty much everything physically. It's why your ice cube sink heavy water is about 10.6% denser than regular water.
Wow, 10.6%. And it affects other things too.
Oh, absolutely.
Wow.
The boiling point is higher, 101.4 degrees Celsius. And heavy water ice actually melts at a warmer temperature, around 3.7 degrees C, not zero.
That's wild. Just from one extra neutron per hydrogen, did that difference, like the heavier isotope, change the chemistry too? Or just the physics?
It does change the chemistry, subtly but importantly. That deuterium makes the bond between the deuterium and the oxygen stronger.
Stronger bonds.
Yeah.
Okay, I feel like that might have implications, maybe biologically.
You got it. And interestingly, some recent studies actually confirm this anecdotal thing people have said for years: heavy water tastes slightly sweet.
Sweet. Huh, but you mentioned biological implications. Is it dangerous?
Well, yes and no. Your body naturally has a tiny amount, maybe equivalent to 5 grams of DO, totally harmless. But get the concentration above, say, 50% in a complex organism?
Then it's a problem.
Yeah, then it becomes lethal. It messes with fundamental processes, particularly cell division. It disrupts the formation of mitotic spindles, the structures cells use to divide.
So bad for us complex life forms. What about simpler stuff?
That's the fascinating part. Many bacteria, prokaryotes, they can actually adapt and even thrive in environments with very high concentrations of DRO, even 100%. Quite resilient.
Okay, so it's this weird, dense, slightly sweet water that's tricky biologically.
Okay.
But it must have some important uses, right?
Oh, absolutely. Critical uses, especially in high-tech areas. Its biggest role is probably as a neutron moderator in certain types of nuclear reactors.
A moderator. How does that work?
It slows down the fast neutrons produced by fission, making them more likely to cause further fission. The key thing about heavy water is that it absorbs very few neutrons compared to regular or light water.
And why is that useful?
Because it's so efficient at moderating without capturing neutrons, reactors using it like the Canadian Candy U design can run on natural uranium. They don't need enriched uranium fuel.
Avoiding enrichment. That sounds like a huge advantage, economically and politically.
It is. And that unique property made heavy water strategically vital early on. Think about World War II. The Allies mounted dramatic sabotage missions against the Norsk hydro plant in Norway.
Why? To stop the Germans from getting it.
Exactly. To hinder their nuclear research program. It was considered that critical.
Wow. So history, energy.
Yeah.
What else? You mentioned high tech.
Right. Beyond nuclear, it's indispensable in science labs, particularly for NMR spectroscopy, nuclear magnetic resonance.
NMR, isn't that for figuring out molecular structures?
Precisely. If you're trying to study a molecule containing hydrogen using NMR in regular water, the signal from the water's hydrogen overwhelms everything.
Right.
But deuterium has a different magnetic signal, so if you use DURO as the solvent.
Its signal doesn't interfere.
Yeah.
You can see the molecule you care about clearly.
Clever.
Very clever. And it's also used in physiology, in something called the doubly labeled water test, using both deuterium and heavy oxygen to accurately measure metabolic rates in people and animals.
Okay, so it helps reveal secrets in chemistry, biology, even nuclear physics. It's all about using its unique properties to see things more clearly or make processes more efficient.
You could say that. Just as scientists use deuterium to uncover complex secrets and optimize these high-tech processes, sometimes you need specialized help to optimize your own systems. This deep dive is sponsored by Embersilk. If you need help figuring out where AI agents could make the most impact for your business, or need help with AI training, automation, or software development, check out embersilk.com.
That's a good link, actually, because that low neutron absorption property we talked about for reactors, it has another really fundamental application.
Oh, yeah?
Neutrino detection. Because heavy water doesn't gobble up neutrons, it's an excellent target material for detecting elusive particles like neutrinos.
Like in that big detector in Canada.
SNO.
Exactly, the Sudbury Neutrino Observatory. The deuterium nuclei in the heavy water there were crucial. They provided the targets needed to interact with neutrinos in ways that allowed scientists to measure all three types or flavors of neutrinos.
So the same property that lets you run a reactor on natural uranium also lets you probe the fundamental nature of the universe. Pretty amazing, isn't it? All stemming from that one little neutron difference in hydrogen. It changes water from the everyday stuff we drink into a key for reactors, advanced chemistry, and even understanding cosmic mysteries.
A simple tweak, profound consequences.
Mhm.
Well, that was fascinating. If you enjoyed this deep dive, please do subscribe to the show. Hey, and if you have a moment, leave us a 5-star review. It really does help get the word out. Thanks for tuning in.